Now let's differentiate between the sulphide, sulphite, sulphate and thiosulphate solutions. If we were to add dilute acid into all these solutions separately, the sulphide ion solution will evolve hydrogen sulfide gas, and we can identify this using different means. The sulphite ion solution will evolve sulfur dioxide gas. There are means of differentiating these two, and then we can differentiate these two likewise. If we were to add dilute acid to thiosulfate ion solution, we will observe not only the evolution of sulfur dioxide but also the precipitation of sulfur, colloidal sulfur. The solution will form a white or yellowish white color turbidity. I mean, with this alone you can identify that it will be the thiosulfate solution. Sulfate, it does not show any reaction with dilute acid. If we were to, however, add dilute acid with a catalyst like tin powder, then the sulphite ion solution will also produce hydrogen sulfide gas. Another way of differentiating all of these is by adding a lead ion solution to these solutions respectively. By lead ion solution, like a solution of lead acetate would do, they will produce their respective lead salts. The sulphide ion solution produces the black colored lead sulphide, while the rest produce their respective white color salts. All of them are white color: lead sulphite, lead thiosulphate and lead sulphate. Now from this we can because it's black, we can identify that it is the, the sulphide ion solution. But here, if we were to add dilute nitric acid into the lead sulphate, this lead sulphite solution, yeah, never forget the name, it's lead sulphite. Lead sulphite. Lead sulphite with dilute nitric acid will dissolve and will evolve sulfur dioxide gas. Yeah, because sulfites with dilute acid will produce sulfur dioxide gas also. So if this step will be rather intuitive. If we were to heat thiosulfates, when thiosulfates are heated, it will produce their respective sulfide and sulfur trioxide gas. It's a unique reaction. So thereby lead thiosulfate will decompose to form the black color lead sulphide and will evolve sulfur trioxide gas. So from this we can identify that it is thiosulfate. Now lead sulphate is white color. It is insoluble in dilute acid like all sulfates are. But if we were to add a caustic alkali, a powerful alkali like sodium hydroxide, or if we were to add ammonium acetate, the white color lead sulfate salt is soluble in them. Now here is a means of differentiating sulfate and sulphites. We do so by adding a barium nitrate ion solution. They will both produce their respective barium sulphate and barium sulphite, both of which are white salts. You can actually reduce the sulphate into sulphite using a reducing agent and oxidize the sulphite into the sulphate using an oxidizing agent like hydrogen peroxide. Barium sulphate is insoluble in dilute acid, because sulfates are insoluble in dilute acids, while the sulphite SO3 2- is not only soluble in dilute acid but also evolves sulfur dioxide gas, because we remember the sulphites with dilute acid, it evolves sulfur dioxide gas. Yeah, here it is. It's a very popular scheme of differentiating between sulphate and the sulphite. Now here are some extra reactions. If we were, this compound over here is called sodium nitroprusside, Na2FeCN5NO. If we were to add sodium nitroprusside in basic medium into the sulphide ion solution, we get this purple color complex, Na4FeCN5NOS. This is a special reaction for determining presence of sulfides in a solution by adding sodium nitroprusside in basic medium. Nitroprusside, Nitroprusside. Here's another unique reaction. If we were to add ferric ions into a thiosulfate solution, we get this complex, a dark violet complex, which is FeS2O3 twice minus, which will then become colorless upon further addition. It will form S4O62 minus, a colorless complex. If we were to add ferric ions into the thiosulfate solution, we will observe a dark violet color, which will then become colorless upon further addition. Now all of these, this is what happens when if you have like cations over here and we bubble hydrogen sulfide gas in it, we will get their respective sulfides. Yes, any cation solution, I wouldn't say any, but cation solutions, when we bubble hydrogen sulfide gas into it, that is basically saying that like we are adding sulfide, it will form their respective sulfide. Yeah, and these cations, they will form the sulfide precipitate in acidic medium. These cations will produce the precipitate in basic medium only. Copper, mercury, lead and bismuth will produce black color precipitate, the black color sulfides, while arsenic, cadmium and zinc 4 plus stannic ion will produce yellow color precipitates, while the stannous ion will produce a brown color precipitate, while this is antimony, and the antimony ion will produce an orange color sulfide. Now in basic medium, if we were to bubble the hydrogen sulfide gas, the copper, nickel and cobalt will produce black color sulfides. Zinc will produce a white color sulfide, and manganese will produce a pink color sulfide, the only pink color sulfide, which is interesting. Okay, in addition to what we discussed, if by chance like there is something about identifying phosphates, like we can do so by adding ammonium molybdenate into the phosphate ion solution, which produces a yellow color precipitate. What we see above, here we do so when we differentiate the nitrites and the nitrates, we do so with ammonium molybdenate with concentrated nitric acid. Here we do so without that concentrated nitric acid. I was confused about that a long time ago, but it's good to have that cleared out. Phosphates with ammonium molybdenate will produce a yellow color precipitate, and that's how you without concentrated nitric acid, and that's how we identify phosphates.